So I want to follow the other speakers in thanking the organizers for the invitation. I lived in Durham for a long time, and as I've told you before, the smell of a Bojangles chicken filet biscuit is like a Madeleine is to Proust. So, okay. Now, this research that I'm going to be telling you about is part of a, I guess, historical approach to research, which involves appending the label applied or computational to the front of an established field of mathematics and proclaiming that you have done something new. So the most successful example of this, of course, is applied mathematics. But we've seen other examples of this, like computational topology and so forth, that have started receiving some currency lately. So I thought I'd give this coinage a shot. Okay, so what is a random matrix? It's, as you know, a matrix whose entries are random variables, and they need not be independent from each other, which is extremely important for our purposes. And I have displayed for you a draw of a random matrix, which does, in fact, have independent entries. Just so you can see what these things look like. And I assert that, in fact, in most applications that you encounter, the random matrices you'll see are a lot more complicated than this one. They might even have more than 4 decimal places. Okay, so what do we want to understand when we try to study random matrices? So what's interesting about a random matrix as compared with a random variable or a random vector is that a random matrix acts on vectors to produce other vectors, and therefore it has spectral properties, namely eigenvalues and eigenvectors if it's square, and in general it'll have singular values and singular vectors. And if you think about this matrix acting between 2 normed linear spaces, then you can also think about the operator norm of the matrix, which is a reflection of the geometry of the 2 spaces as much as it is the distribution of the matrix. And so there's a huge literature on these things. When they come from what I'll call classical ensembles, I'll tell you a little bit more about what I mean in a second. And this is a beautiful subject. There are a lot of beautiful results. And here are a collection of books that describe some of the results that have been developed in the past. And these results are still beautiful, and they're still interesting, and they're still useful. But I assert that we need to go farther. So some of the areas that random matrix theory has historically had played a role are multivariate statistics, beginning with the paper of Wishart from 1927, in which he studied the distribution of the sample covariance matrix of a multivariate normal distribution. Okay? So we call these things Wishart matrices now in honor of this paper. It came up again in nuclear physics in the 1950s when Eugene Wigner surmised that you might be able to use a random matrix to model the Hamiltonian of a heavy atom undergoing a slow nuclear reaction. And that's really what launched the subject into, I guess, prominence in mathematics. And a huge amount of the work on random matrix theory was spurred by Wigner's 1955 Annals of Math paper, in which he studied what we now call a Wigner matrix, which has symmetry about the diagonal and independent entries above the diagonal with mean 0 and variance 1. Okay. It comes up in graph theory, for example, in the Erdős-Rényi model. It comes up in asymptotic convex geometry, in part because of Millman's idea that the probabilistic method, random models, are a good way to produce structures in high-dimensional linear spaces. Montgomery observed that the eigenvalues of a matrix drawn from the GUE describe the zeros of the Riemann zeta function. And it also came up again in operator theory in the 1980s with the work of Voiculescu on what we now call free probability. So there are lots and lots of places this has come up. And in a lot of these cases, these matrices are very special and have a lot of distinguished properties that we don't necessarily expect to find in a garden variety random matrix that we stumble across when we're doing other types of research. So there are a lot of more recent applications of random matrix theory. So these are some areas and references chosen at random, non-uniformly, where I have seen random matrices play a role in recent years. They come up in algorithms for numerical linear algebra, which is something that's close to my heart. They come up now in numerical analysis, uncertainty quantification, and a host of other areas. The application that I think is most interesting is when random matrices are used inside computer algorithms to ensure that those computer algorithms work. So we're harnessing the statistical properties of a random matrix to guarantee that some algorithmic procedure is effective with high probability. Some of these other examples, for example, in high-dimensional statistics, use random matrices as a model for multivariate data, which I think is a more questionable proposition. Other areas like compressed sensing, we use random matrices as sensing matrices, and one hopes that we can design an engineering system that uses that random sensing approach to acquire data. And then there are other areas like combinatorics where you use random matrices to construct combinatorial objects like expanders. But anyway, there are a huge number of places where this comes up. I can't even begin to do justice to these areas. I just want to make the point that random matrices are more ubiquitous than ever, and that researchers doing a lot of different things need to know a little bit about random matrices or have tools that they can use to understand random matrices that they might well come across in their work. So I'm going to define a random matrix model loosely as a class of random matrices that admit a unified analysis, whatever that means. But just think about it as a bundle of random matrices that you can understand all at the same time because they share some kind of structure, some kind of properties. Now, there are three things that you might want out of a random matrix model. You'd like it to be flexible. You want it to describe lots and lots of different kinds of random matrices that you might come across in your life. You would like the model to be easy to use. So there are going to be some summary parameters associated with the random matrix, and you'd like these to be easy to calculate, or at least you'd like there to be some explicit recipe for getting your hands on these parameters so that you can understand the random matrix that you'd like to study. And third of all, you want these models to be powerful. You want them to give you an analysis that's qualitatively pretty accurate. Now, I would argue that these requirements are in competition with each other. So, for example, consider the random matrix model where the random matrix is always equal to the identity matrix. Okay. This model is very easy to use. It's extremely powerful. I can tell you all of the eigenvalues and eigenvectors of this matrix perfectly well, but it's not very flexible. It doesn't describe any random matrix of interest. So you can also imagine a model that's extremely flexible, like my random matrix is a function of some random variables, which describes everything you can imagine. But on the other hand, what kind of summary parameters could you imagine in this case? I mean, is this something you're going to be able to get your hands on? How are you going to analyze these things? And so somehow you're looking for this sweet spot where the model describes a reasonable amount of stuff, but at the same time, it's still specific enough that you get your hands on it, that you can understand the random matrices that are drawn from this family. Okay. So here's some classical random matrix models that you may have seen if you've ever read anything about random matrices. So the three big ones are the Gaussian orthogonal ensemble and Gaussian unitary ensemble, which are part of a larger family. These are matrices that are symmetric and have independent standard normal entries above their diagonal and normal entries on their diagonal. And orthogonal versus unitary is a reflection of whether the matrix is real or complex. Okay? So beautiful objects, very well understood, in part because they are invariant under the action of the orthogonal or unitary group. Okay? Wishart matrices, which we described before, are like sample covariance matrices for standard Gaussian vectors. Also invariant under the orthogonal group, and so we can understand these in a very, very detailed way. There There are also these things called Jacobi matrices that come from compound sample covariance that I'm not going to talk about. Now, these things all have direct extensions that have also been studied. The Wigner matrix is like a fancy version of the GOE, where now the entries don't have to be Gaussian anymore. They can come from some other distribution. Marchenko-Pasteur is sort of like the square root of a Wishart matrix. It's a matrix with independent entries. And its product with its transpose gives you a Wishart-type matrix. And what's interesting about these extensions, and Manova is like a Jacobi matrix. So what's interesting about these extensions is that they behave almost exactly the same way as the invariant models up top, which is one of the triumphs of modern random matrix theory, the establishment of universality laws, showing that larger classes of random matrices behave exactly the same way as the invariant models. And there are lots and lots of other extensions that have been studied. But one thing I want to emphasize is that all of these models are still very special. They're not flexible. They describe a very small number of random matrices in extraordinary detail. And so they have deep connections with a lot of different parts of mathematics. They're very beautiful objects, but they may not be that relevant for some of the problems that come up in the areas that I showed you on 2 slides ago. Okay, so I grew up here in Durham, and I went to school down the road at Charles E. Jordan High School, and I learned that when you give a presentation, you should have a thesis statement that you support with evidence. My thesis statement is that modern applications demand modern random matrix models, and I hope that I can persuade you of this assertion. So let me begin with a model that I think is very interesting and has been useful for a number of applications. This is the independent entry model. So a random matrix from this model has independent entries. They have mean 0, but the variances don't have to be the same. So there's a very big difference between this and the Marchenko-Pasteur model, where all the entries basically have the same variance. Okay? So now you're allowing the variances to differ among the entries. Now, this model is somewhat harder to study because it doesn't have as much structure. But there's a beautiful theorem from last year by Afonso Bandera and Ramon van Handel that achieves an essentially sharp bound for this class of random matrices. So one thing I'd like to emphasize is that when I talk about random matrices today, I'm only going to be telling you about the expected spectral norm of the random matrix. That is to say, the largest singular value or the L2 to L2 operator norm. And the reason is that this is the single most important spectral statistic of a random matrix in applied contexts. If you want to know about other spectral statistics, it might be much more challenging, but for the most part, it's not quite as relevant. So what Afonso and Ramon showed is that you need to compute 2 parameters of the random matrix to understand how it behaves. The first is what I call the matrix variance statistic, which is, there should be expectations inside both of these spectral norms. And this returns the maximum expected squared column norm or the maximum expected squared row norm of the matrix. The second number is just the maximum variance of an entry. So you can imagine if some of the entries vary a lot more than others, you're going to have to pay for that. Okay? And what they showed is that these 2 quantities determine the expected spectral norm in the following fashion. You pay for the square root of the variance, you pay for the maximum variance of an entry, and there's a logarithmic factor that depends on the dimensions of the matrix. And this estimate is essentially unimprovable, which makes it very valuable when you come across a matrix of this form. So one of the applications that Afonso was interested in was recovery of communities in the stochastic block model. And of course, the stochastic block model involves membership in a community with a certain probability and non-membership in a community with a different probability. So if you think about the random matrix describing which entities are members of which communities, the variances of the entries of this random matrix are different from each other. Okay? They have different means, they have different variances. And as a consequence, you can't apply theory for Marchenko-Pasteur matrices where the entry is all of the same variance. You really, really need this extra flexibility to understand the random matrices that come up in this application. And so Afonso has some very nice work where he accomplishes just this using this result of theirs. Okay. Let me pause and ask if there are any questions on this. Okay. So this is still a somewhat special model, but it is more flexible than the classical models and allows you to deal with applications that come up now that people have been extremely interested in. Now, as you generalize, you're going to gain in flexibility, but you're going to lose in precision. And so next I'm going to talk about a model that I particularly like, which I call the independent sum model. So a random matrix drawn from this model is one that can be written as a finite sum of random matrices that are independent from each other. Okay? So in particular, this includes matrices drawn from the independent entry model, where you just think about each one of these as being a random variable times one of the matrix basis elements. Okay? So it's clear that the independent entry model is a special case of this. You can also use this to describe things like sample covariance matrices and other kind of matrix plug-in estimators, where each one of these random matrices is an estimate for a given matrix, and by averaging them together, you get, for example, a sample covariance matrix. This is an extremely flexible and useful model that has already seen a tremendous amount of use. And the theorem I'm going to tell you about in this case is one that in some form or another dates back to work of Nicole Tomczak-Jagerman in the 1970s and proceeds through a beautiful series of papers by Françoise Luce-Picard and Gilles Pizier and a variety of other authors in the asymptotic convex geometry community. But this was really nailed down only just in the last few years. And I think part of that's because we are trying to use these results for applications. And it's really helpful to have very clean, concrete statements of what goes in and what comes out. Whereas in a lot of these papers that appeared before, this was somehow embedded in a larger fabric, and it was a little bit hard to pull out this specific piece. So suppose that Z is a sum of independent random matrices. And we're going to define the matrix variance again. There should be expectations inside these norms. So think about this as the expectation of the square. Since these things are mean zero, it really is like a variance. And we'll define L to be the expected maximum squared norm of one of the summands. Okay? And what this theorem asserts is that the expected norm of the random matrix is controlled again by the matrix variance and by this upper bound parameter, this uniform estimate on how big the summands are, and both of these things now have logarithmic terms depending on the dimension. So you can see this is slightly worse than the estimate that Ramon and Afonso obtained for the independent entry model, but that's natural. It's a more general model. It includes more things, and there are more things that can go wrong. So that's where the logarithm comes from. It turns out this estimate is also sharp. It can't be improved if you do not place additional assumptions on the random matrix. And this result in some form or another through the matrix Bernstein inequality, which is a sort of exponential version of this, has been used in an enormous number of applications, as some of you have probably seen. One application that I think is interesting is a forthcoming paper that Samit Oymak and I are writing, in which we obtain a bound on the minimum singular value of a rectangular random matrix. And we show that you get exactly the value you want, even if the entries of the random matrix only have 2 plus epsilon moments. And you need this tool inside the proof to make that work. It's very, very important that you have this estimate and that it only requires the random variables here to have 2 moments. You have a question? There should be an expectation inside?
Yes.
Yeah.
Isn't it the same as that of the transpose times?
If the expectations inside, no, they're different. they really are different from each other. So matrices of two squares, and in this setting, they're actually incommensurate. They can have completely different magnitudes. One could be equal to 1, and the other could be equal to the ambient dimension, for example. So you really need both pieces. Okay. Since we're running a little low on time, I'm going to move on to an even more general model, which, as you may expect, is more flexible, but is harder to use. So this is what I call the independent input model. So a random matrix from this model is one that has mean 0 and can be written as a function of some independent, say, scalar random variables. So they're independent inputs that go in, and a random matrix come out. Now, you can imagine this is an extremely general kind of construction. Almost any random matrix you imagine can be written in this fashion. And so, as you will guess, the theorems are going to be less impressive. But there are theorems. So, for example, you can prove a bounded difference inequality. So if you can show that changing one of the random variables doesn't change the random matrix by very much, then you can show that the expected norm of the matrix is not so big as compared with the total amount of change that you can incur by changing the variables one at a time. This is a lot like the bounded difference inequality for scalar random variables. And this comes up in machine learning. It applies to the analysis of the confusion matrix in multi-class classification, where when you change some of the input data, the confusion matrix can't change that much when you perform the validation. And so this kind of tool is relevant because it's a very complicated function that describes how the confusion matrix is related to the input data, but nevertheless, it has these bounded differences. And this was a paper due to Morvant et al. In 2002 in which this application appeared. I think there'll be a lot more applications of this type of bounded difference inequality, but it hasn't really been widely advertised, and so and it perhaps has not entered people's consciousness. And I want to mention one other result that we developed this year, which is a sort of extreme extension of the bounded difference inequality, which we call the matrix Effenstein inequality. So this is joint with Daniel Pollan, a postdoc at NUS, and Lester Mackey, who's an assistant professor in statistics at Stanford. And both of them are really the drivers behind this result. So in short, if changing one entry of the random input doesn't change the random matrix very much on average, then, as before, you can obtain an accurate bound on the expected norm of the random matrix in terms of the expectation of how much a change in the inputs affects the random matrix. Now, this can be applied to study compound sample covariance matrices, and I'm actually not aware of another approach to this problem aside from this tool. Again, this is a relatively new result, and it hasn't really seen very much application yet, but because of the generality, it applies to a huge variety of examples that may not be accessible to other methods. On the other hand, it's a little bit of a pain to get your hands on this quantity and to understand it. And so this is the tension I was describing. It's flexible, but it's not so easy to use. And part of the goal of this new field, I think, of applied random matrix theory is really to find the sweet spot in this collection of tools, to find things that apply to good examples that we can use to summarize those random matrices simply and that give useful, accurate results. So I got a little obsessed with this topic, and I've written a few papers on it by now, in which some of these results and some others I didn't talk about appear. And I really hope that the collection of methods that I've developed over the last 5 years with my co-authors and students allow people to understand algorithms, to understand statistical models, to understand problems that have been inaccessible to classical statistics. And I also hope that these tools are useful for people who don't have a doctorate in random matrix theory. That's one of the other major goals here, to make this accessible to researchers who have other primary interests. And I don't know if I've succeeded, but there's a hope, and there's still a lot of work to be done. Thank you.